All right, so let's start solving some exponential and logarithmic equations. And in order to do that, we want to look at a property that applies to both of them. That's a pair of properties, one for exponential and one for logarithmic functions, actually. It's called the one-to-one property, or they're both called the one-to-one property. And in one case, you have the one-to-one property of exponential functions, and in the other case, you have the one-to-one property of logarithmic functions. And they both have the same eliminated values, or the cautionary values, which are that b, and in a moment we're going to be talking about b as the base, b has to be greater than 0. So we're not working with negative bases, and the base can't be 1. And in a second, it should become pretty obvious why that's true. So the one-to-one property for exponentials says that if I have any base raised to a power and it's equal to the same base raised to another power, that this can only be true if m equals n. If and only if m equals n. And in fact, the if or only if means that it's a two-way, drop my pen. Can't hang on to my pen. It just means that it's a two-way street. So if m equals n, then I could put them above any base and I would have still have an equation or an equality. Or if I have the same base on both sides of an equal sign with different powers, that those powers, though they may look different, still have to be exactly the same. So that's the exponential version. And then the log version of the same property just says that if I have a log base b of m equal to the log base b of n, then again, the exact same thing. N has to equal n. So we're going to use these to solve a couple of equations. Number one, we're going to solve 4 to the x plus 2 equals 16 to the x minus 3. So using the one-to-one property of exponentials, if I can get them both to have the same base, then I can just take the powers separately to solve for x. And I can certainly do that because this would be 4 to the x plus 2. But 16 is really just 4 squared. So I can say 4 to the 2 times x minus 3. And now I've rewritten it as two equivalent expressions on either side of the equal sign. I can just pull down. Since I have the same base, I can just set m equal to n. So I get x plus 2 is equal to 2x minus 6. Subtract 2 from both sides, I get negative x is equal to subtract 2 from both, to subtract 2x from both sides, I get negative x. Subtract 2 from both sides, I get negative 4. Take the opposite of both sides, and I get x equals 4. Couldn't be simpler than that. So easy to do. How about, let's do this. Let's find 2 times the natural log of x equals 18. Okay, so what do we have here? Well, first off, I think I want to simplify by dividing both sides by 2. So I end up with the natural log of x equals 9, just to make it easier to see. Now, this next part isn't naturally, it's not instinctive to have thought of it, but really, if we remember that we have a property from before that says the natural log of x, if I had the base e raised to the natural log of x, this can come out, right? It equals 1, and I would just be left with x. So let's make use of this in order to make use of the one-to-one property. So if I take both sides, if I raise both sides over e as a base, then the natural log of e disappears and I'm left with x equals e to the 9th power. And I can finish here if I want an exact value, or I could put it into my calculator, and I might have already done it. Yes, e raised to the 9th power equals 8103, or approximately I should say, equals 8103 point, and let's go with 3 decimal places, 084. Couldn't have been easier than that. Even though I think when we first looked at it, we might have thought, oh, that's going to be way too hard to solve. But bearing in mind all the different properties we have to work with, just looking for the simplest way to get our value of x out of whatever expression we're looking at, whatever equation we're looking at. Let's do another one, number 3. Let's take 7 minus 3 log of 10x equals 13. So now, step back before you start working. Let's isolate the log 10x first. So that means I'm going to subtract 7 from 13 and then divide by -3. So I'd be left with log 10x on one side. Well, 13 take away 7 is 6, divided by -3 is a -2. Okay, so it's all cleaner and I've isolated my logarithm on one side. And let's think, what can I do? Well, what I want to do is I want to figure out some way to use my property, but I'm certainly not there yet. I could certainly use this side, which is to figure out to raise it to some power. So if I can raise both sides to the same power, maybe I can get to, I can cancel out my log and then be just left with using this property, the one-to-one property for exponentials. In fact, I think that's exactly what I'm going to do. I know that if I have the log with nothing written, that it's a 10, the base is 10, so I'm going to raise both sides over the base of 10. Once I've done that, once I've elevated that, I get rid of the log and the 10 on the left-hand side, and I'm left with 10x equals 10 to the -2. So 10 to the -2 is 1 over 10 over 1 with 2 zeros. Now I'm going to divide by 10, which means multiply 100 by 10. So I get x equals 1 over 1,000. All right, another example, 4. I think just a bunch of examples will help make this as clear as possible. I have log base 2 of 5 equals log base 2 of 10 minus log base 2 of x minus 4. Okay, so I almost have my logarithmic one-to-one property, except on this side I have a subtraction of 2 logarithms. They're the same base, but I don't really have just a pure log on one side and a pure log on the other side. But I do have previous property. That's the one that reads that if I have log base b of m divided by n is equivalent to log base b of m minus log base b of n. And I just want to work in reverse order. I have the right hand side, I'm going to move to the left hand side. So when I do that, I get log base 2 of 5 equals the log base 2 of 10 divided by x minus 4. Now I have my one-to-one property. Because I have the same log on both sides, I can just set these equal to each other. I can set m and n equal to each other. So 5 equals 10 over x minus 4. If I cancel a 5 from both sides, I get a 1 on the left-hand side and a 2 on the right-hand side. And now multiply through by x minus 4. Well, x minus 4 times 1 is just x minus 4 equals 2. So x equals 6. Easy peasy. How about another example? Log base 5 of x squared plus x equals log base 5 of 20. Okay, again, looks a little bit tricky, but certainly just using the one-to-one property, I get x squared plus x equals 20. So x squared plus x minus 20 equals 0. And so I factor to plus 5 minus 4. So x equals -5 and positive 4. I'm a little bit concerned about this -5 because I know when I'm dealing with logarithms, negative numbers can be problematic. But if I look back up here, if I were to just check it by plugging it back in, if I look back up here, I'm going to see that negative 5 squared becomes positive, and even though I would have to subtract negative 5, subtracting a negative 5 is never going to be as big as squaring a negative 5. So no matter what, I'm still going to end up with a positive value. And I can always take a logarithm of a positive value, so not a problem at all. So let's look at an example like 2 and 3, only one that I start with an exponential rather than a log. So notice in 2 and 3 I started with a logarithm, and then I converted them to exponents by putting them over a base. Let's look what happens if I start with an exponential and see if I might be able to do something similar. So example 6, I want to solve 3 to the x equals 7. Well, in this case, I could get rid of this 3 if I were able to raise this side to the log base 3. So log base 3 of 3 to the x, totally legal as long as I do it to the other side too. So log base 3 of 7. So this cancels and I get x equals log base 3 of 7. That was pretty snazzy, I think. This is a process called taking the logarithm of each side, and you can choose any base you want as long as it's the same base on both sides. Now at this point, I could put this in my calculator, except remember, my calculator can't put in a log base 3. Some of the new ones can, but mine can't. So I have to make a conversion. I'm going to choose to do natural log, and the only reason I do that is because I have a natural log button on my plate, on my faceplate. I don't have to go to my catalog to try to find the natural log. It's already there. So I'm going to take the natural log over the natural log as long as I'm changing the base formula. As long as I keep the numerator and the denominator with the same base, and natural log is definitely the same base. And then the 7 is up high, so it goes on top, and the 3 is down low, so it goes below. And so if I put this in my calculator, I have the natural log of 7 divided by the natural log of 3. Oh, and I didn't ask for a decimal. There it is, 1.77. Let's go 3 decimal places. 1.771. So let's look at a slightly more complicated version of number 6. In this case, I want to solve 4 raised to the 3x minus 1 is equal to 3 raised to the 2 minus x. Okay, well, if I took the log of both sides, certainly legal to do that, is it going to make things nicer for me? Well, at first glance it seems like it might not because I don't have the same base, but in fact if I choose the natural log of 4 to the 3x minus 1 and set it equal to the natural log, just taking the log of both sides, of 3 to the 2 minus x, now I can at least take the monkey out of the tree on both sides. So I can get 3x minus 1 times the natural log of 4 equals 2 minus x times the natural log of 3. So the next step is not very instinctive. No matter what you do, there's no way for us to get rid of our natural logs because they're not the same base, or excuse me, they don't have the same value. They both have the same base, but they're not of the same value. And because I have all of this gobbledygook going on in front of them, I can't find anything equivalent about the logs. So what I have to do is distribute my natural log 4 into 3x minus 1, and then distribute my natural log of 3 into the 2 minus x. And in a minute you'll see why that works. So I have 3x times ln 4 minus ln 4 equals 2 ln 3 minus x times the natural log of 3. Whoops, excuse me, 3. And the reason that works is I'm trying to solve for x. And the only way to get these x's out of here, out of these parentheses and over on one side of an equation, is to do the distribution. So now I can put my 3x natural log of 4, that was badly written, and my x natural log of 3 on one side of the equation in the great hopes that I can factor out an x and move everything else to the other side. So let's do that. Let's keep 3x natural log of 4 on the left-hand side, so I'm going to add x natural log of 3, and then on the other side I'm going to keep 2 natural log 3, and I'm going to add natural log of 4. Okay, looking pretty good because I can clearly take that x out. I can factor the x out of both terms. So on this side I'm left with 3 ln 4 plus ln 3 equals this side. I'm going to do one more step on the left-hand side before I bring the right-hand side down. So now I have x, I'm going to put the monkey back in the tree, ln 4 cubed plus ln 3 equals natural log of 3 squared plus natural log of 4. And now if I simplify this or divide through by both sides, I get x equals natural log of 9, because that's going to be easier to put in my calculator, plus the natural log of 4 divided by the natural log of 4 cubed, 4 16 64, plus the natural log of 3. And I think before I even try to put it in my calculator, I'm going to use another property. I'm going to condense this, so my numerator becomes the natural log of 9 times 4, so the natural log of 36, divided by the natural log of 64 times 3. Yikes! 60 times 3 is 180, and 4 times 3 is 12, so 192. And I could go a little bit farther and say, oh, I can't go any farther. It looks like a property, but it's not. So if I put this in my calculator, I end up with it, x being approximately 0.68. So a bunch of gobbledygook. You may recognize this process here as being very similar to other processes where you have something that has to be distributed in to a binomial or some polynomial before you can separate out the terms containing x and solve for x. Well, I think that's just about enough of that for today.